elements and then we put a complement to each one, or that's something else?
Right.
That's a dual.
Yeah.
So there's two ways to look at the dual. The graph, you can either take the complement of each matroid, or you can take the, if it's a graphical matroid, you can do this.
Right. So the main theorem that we proved last time is that for graphical matroids, you can take the duals in two ways. You can just make the list of bases and take the complements, or equivalently, you can just draw your graph as a plane graph, and then take the graphical dual, and then take the basis of that. Those are equivalent. Okay, so we're going to keep talking about duality today. So 2 classes ago, I showed you that what duality meant for linear matroids. And we said that it goes from a subspace to its orthogonal complement. And then in the class before this one, I showed you how duality works out for graphical matroids, and how for a plane graph, the notion of matroid duality and the notion of graph duality are the same. What I want to talk about today is duality for our third big class of matroids that we keep talking about, duality for transversal graphs, for transversal matroids. Duality and transversal matroids. This is the other big class of matroids that we have, and we would like to know what duality does in this case. And so what I'm going to do is I'm going to define something for you. So let's say that you have some directed graph. And what this means is that every edge of the graph has a starting point and an ending point. So there's a direction on it. We draw it with an arrow. Okay? So maybe I'll draw a directed graph. So just draw your own graph, because it's going to take you a while to draw the same one that I drew. So there's a directed graph. There's vertices, there's edges, and each edge has a direction. Okay? You might have something like this. So sometimes you might have 2 parallel edges that point in different directions. That's fine. So I'm going to define something called a routing. Well, so before I do that, let's say x and y are sets of vertices. Let's say each one has r vertices each. Okay. So maybe, I don't know, maybe x consists of this guy and this guy, and this guy, and this guy. So this is x, and then I'm supposed to pick 4 vertices that I call y. So let me pick this one. Let me pick, let's see, what else should I pick? This one. You might repeat if you want. I'll pick this one, and I'll pick this one. So now, for example, in this case, you have 4 black vertices, 4 red vertices, and the question you're going to ask yourself is, can I draw a routing from black to red? And a routing means what you might think that it means. I want 4 paths that start in a black spot, end in a red spot, and don't cross each other. That's a routing. Okay, so a routing.
You mean you want to connect each black dot to a red dot without...
You want to connect each black dot to a red dot, and you want the paths that you take not to intersect.
Yeah.
So a routing from X to Y is a set of R paths in the graph, which start at X, end at Y, and have no vertices in common. So no 2 of them have vertices in common.
What about, and you have to go along the directions.
So a path in a directed graph is a path that goes in the prescribed directions. No 2 paths have vertices in common. Okay. So for example, in this case, is it possible to do this? Is it possible to draw 4 paths such that each one starts in a red spot, ends in a, each one starts in a black spot, ends in a red spot, and the 4 paths don't cross each other?
Can it, a path is a set of vertices?
A path it's basically a walk. It starts with a vertex, and then you walk around the graph.
But do you list it as a set of vertices? Because I mean, you have those 2 that are the same one, so are they already connected? Since this...
So a path could be empty.
Yeah. Okay.
So for example, you could consider the path that starts at this black dot and ends at this red dot. That's a perfectly valid path. Kind of a boring one, but it's a path. Eric.
Can they share edges, the 2 paths?
They can't, because if they share edges, then they share vertices also, right?
I understand.
Yeah. Yes, you can.
You can, right? If you stare at this long enough, you'll see how to do this, and there might even be several ways of doing it. But one of them is to go like this. I start here, and I go over here, over here, over here, over here. That's one. And for this one, I just stay put. Stay put. It's my second path. For this one, I can go over here and over here. And for this one, I can go over here and over here. Okay. So that's a routing. Routing from X to Y. Any questions about the definition of routing? Again, I don't want to define formally what a path is, because I think I'll just confuse you more. A path is just walking around like you would expect.
But that path with the 2 vertices on top of each other, they have a vertice in common.
No, this is a path that just goes like this.
Yeah, so they have a common vertice. That path has common vertices.
No, because the definition is that no 2 different paths can have a vertex in common.
Oh, I see.
So like this one and this one don't cross, this one and this one don't cross. But you're allowed to start at a vertex and just stay there, if that vertex happens to be in X and in Y. Okay. Maybe I'll say that here.
So
A
there's
path.
nothing else that you could, if we didn't want to have that one stay put, then it wouldn't work. Nothing else could go there because they would have that vertex in common. Like if we wanted to send black to the red on the right.
Yes, that's a very good point, actually. If you have a vertex that is in both X and Y, then the path is going to have to start there and end there. Because if you start another black vertex and end at a red vertex over here, then these 2 paths, then the one that starts at this black vertex is going to have a vertex in common with this one. But it could be a loop, right? It could be. I mean, I could have something like this. And then this could be my routing. But the point is, if a vertex is in both x and y, then it has to be its own starting point. A path might have no edges. That's allowed. Okay. So that is routing. And so this might remind you a little bit of transversal matroids. Yeah. In a transversal matroid, what you have is a bunch of vertices on the left. A bunch of vertices on the right. And then you have, I don't know, the graph looks like this in some way. Actually, I think I want these guys to be the black ones for what I'm going to say. And so remember, what is a basis? It's a subset of these guys that can be married to all of these guys. So that's a bad example, because this is impossible. But maybe this is a better example if I do this.
And each of those is also called full transversal?
I'm sorry?
Each of those bases would be a full transversal?
So remember, what is a full transversal? It is, in this case, a full transversal is a collection of 3 vertices, 3 black vertices that you can match to the red vertices. So for example, a partial is a subset.
Sorry about that. Just one more short thing. When we just define a bipartite graph, we say like, what is it, G of L comma R?
Mm-hmm.
What is L the red set and R is the black set? Or
Right, so this is L.
Yeah.
This is R. So, for example, what's a basis? A basis is taking the top 3 guys, because you can marry this one to this one, this one to this one, and this one to this one. Okay. So you see this picture is not too different from the picture over there. It's a little bit different, not too different.
Are the colors?
It's a little bit different. I'm not claiming that this is a special case of this. All I'm claiming is that if I happen to color these guys red and these guys black, then you might agree that this is somewhat similar.
I guess we have to make more clear what the roles of X and Y were over here.
Right, so I haven't told you how to define a matroid here, and that's exactly what I'm going to do now. It's a theorem of Mason. From 72. Mason said, if you give me a directed graph, I can define a matroid for you. And the matroid goes like this. So this guy be a, you'll see this sometimes. Sometimes people write digraph, and this means directed graph. Okay. So I give you a fixed graph, and I give you a set of vertices. B0 is a fixed set of vertices. Okay. Now I'm going to define a collection L of G comma B0. Let's say that there's R vertices here. And the collection is going to consist of the sets of initial points x for which you can find a routing to be 0. So the collection of, so you take an R set X, and this guy is going to be a basis of the matroid if there is a routing from X to be 0.
So wouldn't that, in your two pictures, wouldn't that make the colors be the other way? Or am I confused?
I think the pictures kind of match if you direct the edges in this direction. And you think of this as B0.
Oh, okay.
So
And you think
B0
of
is not a, it's not a basis, it's a fixed set of R vertices
B0 is a fixed set of R vertices in your graph.
in your graph.
Okay. And you're going to ask yourself, what can I route to B0? The things that you can route to B0, those are going to be the basis of this matroid.
Can I think of B0 as a Y here?
Exactly. B0 is exactly playing the role of Y there. So here's an example. I give you a fixed graph. I give you a collection of 4 red vertices. And I ask you, which collections of 4 black vertices can you route to the 4 red vertices? Those sets are going to be the basis of a matroid.
Sets of black.
The sets of black vertices that you can route to the fixed red vertices. So maybe it's a little clearer if I even put this B0 in red so that you know you should be thinking of B0 as a fixed set of red vertices.
And that set itself is always there too, right? The B0 set, because of, it's just like the guy up there.
Right. Right, so what Jameson is saying is that, for example, I immediately know that there's one basis of this matroid, which is B0 itself. If I fix a set of red vertices, is there a routing from the set of vertices to itself? Well, yes, there's the obvious routing that says each vertex, each path is empty. Okay. But you're going to fix the red vertices and see which sets of black vertices you are able to route to the red ones.
So you don't distinguish that between which black ones go to which red ones, though, in this definition you just.
That's right. So this definition doesn't notice which black vertex went to which red vertex. It just says which sets of black vertices can you route to which sets of to the fixed set of red vertices. Eric, question?
So it might be in there, but it needs to kind of exhaust B naught, though, yeah? I mean, it has to go to every element to be a basis.
So this is implied by the definition because B naught has R vertices, and I'm defining these to be R sets. And so you do have to exhaust B0. You have to have a path going to each red vertex.
Is there a way to kind of formalize this in terms of mapping? I mean, I'm sure there is, right? Conditions on the map, I mean, it's rejected.
Yeah, so you can probably phrase this in terms of functions on this graph or something like this. I personally think it's going to be easier to think about this in terms of the picture of the graph, just walking around it. So the theorem is that this is a matroid. So these are the bases of a matroid. Theorem, these are the bases of a matroid. This is the collection of bases of a matroid. Of a matroid on V.
When you said this, you refer to LG and not B number.
L of G B0. Yeah. Right.
And this type of a matroid is different from the types of graphical matroids we've looked at before, because this is a matroid on V and not B.
That's a good point. This is definitely, by definition, not a graphical matroid. It might turn out to be a graphical matroid, but Before we had a graph, and we defined a matroid where the elements were the edges of the graph. But here, I have a graph, and the elements of this matroid are the vertices of the graph. They're the possible black vertices that you want to choose. Okay. Now, I want you to see that this is a little bit similar, but not the same. Transversals. In a transversal matroid, you can think of the left vertices as the red vertices. Okay? You can think of all the arrows pointing from right to left. And so, for example, in this transversal matroid, these three guys form a basis. These three guys form a basis because I have a matching. And a matching is a routing. Okay? But a routing doesn't have to be a matching. Okay? Why? Because this graph is bipartite, and this graph is not bipartite. And so, for example, in this graph, I have a routing from the red vertices to the red vertices. And so in the transversal matroid, these three guys are a basis. But if I think of the matroid that I'm defining here, then, for example, this guy, and this guy are a basis of, I'll tell you, these guys are called cotransversal. So this is a cotransversal matroid. If I look at the same graph, then, for example, these three guys form a basis of the cotransversal matroid because I have this routing that goes like this, and this guy stays put. So here I have a basis of the cotransversal matroid that is not a basis of the transversal matroid. So you should be thinking that these two are similar to each other. They are a little bit reminiscent of each other, but there is a difference between routings and matchings. And these two guys are definitely not the same matroid. Okay? So these matroids are called cotransversal matroids. And there's another word that you might see in the literature. They're also called strict gamoids. Matroid theory is full of ugly words. And I think most people prefer to use cotransversal, and that includes me. You won't hear me say strict gamoid in this class, but if you ever see it written, then you know a strict gamoid is what I call a cotransversal matroid. Okay? Why were they called strict gamoids originally? Because people didn't know that this theorem was true. Theorem. Cotransversal matroids are exactly the duals of transversal matroids. If they're going to be called cotransversal, then you hope that there's a reason for that, and that's exactly the reason. The duals of transversal matroids. People saw this definition of this matroid L of G comma B0, and it really sounded like transversal matroids, and they were wondering what the exact relationship was, and it didn't take too long. So this is a theorem of 73 of Ingleton and Biff. So this is the precise relationship between transversal and cotransversal matrix. Okay. So what does this mean? It means if you give me a transversal matroid, then I'm able to build for you a graph such that this L of G B0 for this graph is the dual of the one you gave me. So for each transversal matroid, the dual has this form, and every graph that arises of this form is the dual of a transversal matroid. Okay. And so this completely explains duality in transversal matrix. Okay. Any question about this statement of the theorem? I'm not, well, so probably by now you noticed that, or some of you have noticed that one of the exercises in the homework is precisely to prove this result of Mason, that cotransversal matrices are actually R matrices. So this is one of the problems in the homework, and that's why I'm not going to prove that for you in class. And this theorem is harder than. Question, Susan.
Federico, I actually got lost at when you drew the second picture there. How do you construct a cotransversal from a transversal? That was the part that was. I'm thinking of going from a matroid to its dual. I mean a graphic, like a planar graphic matroid to its dual. I was looking for something like that here.
So the question is, how do you go from the transversal picture to the cotransversal picture that it corresponds to? I can
Did you do that there, or was that just?
No, I didn't do it. So
That's not the cotransversal corresponding to that transversal, is it?
Okay.
no. So right. So maybe I should say that clearly, that I don't mean to say that if this is the transversal matroid, then this is the cotransversal matroid dual to it. This is not at all true.
So then what is cotransversal? I'm sorry if I'm stealing your question, but I think we have the same question.
And I think that it has to do with the idea of a routing and a matching, is what we were talking. The significance is maybe.
Right. So all I meant to say when I put these two side by side is that routings and matchings are similar to each other,
But not the same.
but they're not the same. Okay.
So here's an example of something that can happen in cotransversal that can't happen in a transversal.
Right. And actually, there is a second relationship between transversals and cotransversal matrices that we're going to discuss in the forum. I don't want to say that here, but I want to outline more. I want to say more in the forum about this picture, and so we'll talk about that there. But I haven't told you. If I tell you, okay, every transversal matroid is dual to a cotransversal matroid. So here's a picture of a transversal matroid. The question is, how do you draw the graph for the cotransversal matroid that is dual to it? I haven't told you that. So no need to worry about that. And actually, I wasn't planning on I was just going to give you a very brief sketch of this proof and propose this to you as a project also. Now, if you guys decide among yourselves that you really, really want to see this proof, then I can show it to you next time. But I wasn't planning. I'll give you an outline of the proof, and then you can decide if you want to see it or not next time. So here's an outline of a proof of this theorem, of a proof of this theorem.
Well, this is a homework question, right?
Now, so this is a homework question too. But I'm talking about this theorem, that cotransversals and transversals are precisely dual to each other. I have a favorite proof of this just because it happens to be my proof. So this doesn't mean that it's the best proof, but it's the one I like the most. I don't know. And if you want to see it completely, you can. It's on my website. So there's a picture, a paper called Transversal and Cotransversal Matroids, blah, 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 blah. It's on my website. This is from last year. But I'll tell you basically what the idea is. It goes in 3 steps. Yeah?
This isn't the proof that they originally said in 3, is it?
No, this is a different proof from the original. So the first step of this proof is something that is known already, which is that transversal matroids are linear. Okay. I haven't shown you this, and again, so if you wanted to see this proof, then the first thing that I would show you is that transversal matroids are linear. This is not too bad. This is not too difficult. But so if I have a transversal matroid that gives me some vector space in Rn that represents it. It's the first step of the proof. The second step of the proof is something that I discovered and then it turned out that it was also known that cotransversal matroids are linear, and that there is a very nice way to represent them also. So you can find a nice guy that represents them. And this is a little bit of algebraic combinatorics. If you remember, I talked about Kirchhoff's theorem that shows you how to count using determinants. This uses another result of this type, that if you want to count the number of routings, you can just compute a certain determinant, and that tells you the number of routings. So this is a fact in algebraic combinatorics. And then the point is that we understand duality in linear spaces. So if I look at the vector space representing this guy and the vector space representing this guy, and if they're supposed to be dual matroids, then these guys should be orthogonal complements. And so this is the third step of the proof, is to see that the V's that appear in 1 are precisely the orthogonal complements of the W's that appear in 2. Are the orthogonal complements
So being linear means it can be represented as a real in a real Euclidean space?
Being linear means that it can be represented in some vector space.
And if it can be represented
And,
in some vector space, then
And it's a fact that for these guys, you can actually do it over the reals. Okay. And so this is part of the proof, is to say you can actually do it over the reals. You can do it over the reals. And the things that appear here are exactly the orthogonals of the things that appear here, are the orthogonal complements of the W's that appear in 2. So this is basically how this proof goes. And again, so my plan was to propose this to you as a project to understand this. And to study the linear representations of transversal and cotransversal matrices. So it's a project that you could do, but if you guys are really curious to see this, then talk amongst yourselves, decide it, and let me know by tomorrow, and I should prepare it and give it and tell you guys how this goes next time if you really want to see it. But this is, I think, the simplest proof that I know of this theorem.
Studying linear
representation.
Linear representations. Sorry.
Sorry.
Reps. So this is how duality works out for transversal matrix. Okay. Okay. And this is the end of duality for now. So we're going to leave duality, and I'll tell you what the next thing is that we're going to do. The next goal is to talk about some other notions that appear in Matroids. Okay? So there's a notion of rank that you may have already wanted to say what rank means. So there is a notion of rank in Matroids. There's a notion of closure that you maybe this is a little bit harder to guess so far what closure should mean, but we have a closure relation in Matroids, and from there we're going to define something called flats. Okay? Lattice of flats. And this is going to take quite a bit of work to get there. And so my plan for the rest of today was just to motivate this and tell you what we're trying to do in defining this lattice of flats. What is this? Okay. And a good motivation for this comes from the theory of hyperplane arrangements. So this is what I'm going to show you now. So I already defined for you a hyperplane arrangement, and you guys already proved that a hyperplane arrangement gives a matroid. But I haven't really drawn for you what a hyperplane arrangement might look like. Part of the problem is that these things are very difficult to draw. The farthest we can go is 3 dimensions, or there's a trick for drawing in 4 dimensions, which we'll see. But for now, let me draw for you a hyperplane arrangement in R3.
That sounds hard to draw too.
This is hard to draw. It's not easy. I really had to rehearse this picture before coming here today. So a hyperplane arrangement in R3 is a bunch of planes. Okay? So here's one plane. And I mean, of course, this extends infinitely, but I'm just going to draw a triangle of it. Here's another plane. And here's another plane. So these are 3 planes that have a line in common. Let me number them 1, 2, and 3. You're okay so far?
And they're not necessarily subspaces.
I'm sorry?
They're not necessarily going through the origin. Are they?
They are.
The origin
I mean,
might be here,
hyper-
for example.
But are your hyperplanes
Linear.
subspaces?
Yeah.
Do they have to go through the origin?
So actually, the arrangement that I'm going to draw for you is not a linear hyperplane arrangement. So, well, you'll see. So I'm going to draw 2 more hyperplanes for you. The other one that I'm going to draw is this one right here. You see it? So this is hyperplane 4. And you can see that I already formed another one under here. Hyperplane 5.
So your have sort of.
So what I have now is basically a tetrahedron,
Yeah.
and I have a plane cutting through it, which is plane number 2. Okay. So here's the tetrahedron. It's the outside thing, and then plane 2 is cutting through it.
Why not that the plane 4 and 5, they add up as triangle?
This is just one possible example. I mean, if I,
Yeah.
of course, there's infinitely many examples that I could have drawn, but I just want to consider this example right here.
Aren't planes 4 and 5 the same plane?
No, 4 is sitting like this, and 5 is sitting down here. So 5 is the bottom face of the tetrahedron, and 4 is this face right here.
So four of the hyperplanes are faces
Thanks
of
for
a
asking.
of a
Exactly. So
tetrahedron.
you see the faces of the tetrahedron are 1, 3, 4, and 5. And then 2 is this thing piercing through the middle. Okay, so it's very hard to draw, very hard to visualize. But I mean, that's part of the point. The point is we're not going to take this theory of hyperplane arrangements very far if we're going to rely on pictures, because it's just impossible. So what I'm going to do is draw, associate to this a combinatorial object, which is called the intersection lattice, intersection poset. So what I'm going to do is I'm going to record all the possible intersections of all the hyperplanes in a picture. So for example, what are the two-dimensional planes that you see here? Well, we have names for them already. There's 1, there's 2, there's 3, there's 4, there's 5. 1, 2, 3, 4, 5. Those are the planes. How many lines do you see in this picture? Stare at it for a while and tell me how many there are.
7.
There's actually 8 lines in this picture because a tetrahedron has 6 edges. And then there's this guy, and there's this guy. For example, what should I call this line right here? Well, you see that's the intersection of plane 1, plane 2, and plane 3. So I'm going to give that guy the name 1, 2, 3. It's this line. Okay. Then,
Which one is it again, Federico?
so 1, 2, 3 is this line right here, because it's the intersection of plane 1, plane 2, and plane 3. What should I label, for example, this one down here?
It's going to be 5 and 1.
It's
Yep.
1 and 5. So 1, 5. And then, of course, there's many other ones. So I'll tell you what they are. You have to do this carefully to make sure you don't make mistakes, but these are all of them. 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. Here you don't have to be too careful, because any two planes intersect in a line.
So you might just list the same thing twice.
So I basically get all the pairs of hyperplanes, except that 1, 2, and 3 intersect in a line together. So that's why this is the only one that's different from the other ones. Okay. How many points do you see in this picture?
Not as many.
Don't look at this side. This picture.
Oh, points.
Four.
Sorry.
Well,
5.
5 points, right?
It's the one
the one in the middle
in the
of
middle.
For example, what should I call this point? Well, this is the intersection of plane 2, plane 4, and plane 5. Okay, this takes time to stare at this picture, but for example, what should I call this one back here? 1, 2, 3, 5. Because the planes going through this point are plane 1, plane 2, plane 3, and plane 5. The only one that doesn't go through it is plane 4, which is this other face of the tetrahedron. This guy up here, you have 1, you have 2, you have 3, and you have face 4. And you do this in all possible ways. So I like to do these things alphabetically. So 1, 2, 3, 4 should come before 1, 2, 3, 5. And then I should have a, what should I have? A 2, 4, 5, 1, 4, 5, and a 3, 4, 5. Is there anything else that you would put here?
Well, the whole thing in an empty set.
Here's R3. So it's the empty set. No hyperplanes. Hyperplane 1, hyperplane 2, so on. Now I'm going to draw some edges in this picture. And I'm going to draw them in the way that you would probably do it. For example, what should I connect my 1 to on this floor? So I'm going to connect it to 1, 2, 3, to 1, 4, to 1, 5. Because 1 is contained in 1, 2, 3, in 1, 4, and in 1, 5. 2 is contained in 1, 2, 3, 2, 4, 2, 5. 3 is contained in 1, 2, 3, 3, 4, and 3, 5. 4 is contained in 1, 4, 2, 4, and 3, 4. 5 is contained in
You missed 4, 5.
Did I miss something?
4, 4, 5.
4, 5. And 5 is in 3, 5, and 5 is in 4, 5.
And 1, 5.
No, 1, 5.
And 1, 5. Thank you. Now, where's 1, 2, 3? 1, 2, 3 is contained in 1, 2, 3, 4. It's contained in 1, 2, 3, 5. 1, 4 is in this one. 1, 4 is in this one. 1, 5 is in this one. And this one. 2, 4 is in this one. And this one. 2, 5 is in this one. And this one. 3, 4 is in this one and this one. 3, 5 is in this one and this one. And 4, 5 is in this one. And this one and this one. And the empty set of hyperplanes is in all of these. Why do I not want to put a 1, 2, 3, 4, 5 here? Because the intersection of planes 1, 2, 3, 4, and 5 is empty. And this is called the intersection poset because it's the poset of intersections. The empty set is not an intersection. So this is called the intersection poset. Okay? Now, this is something that you could actually, if I gave you the, I mean, this is something that you could do even if you cannot draw the picture.
Can you explain a little bit why the empty set? I'm just missing something here. So 1, 2, 3, 4, 5 on the bottom.
So here what I'm doing is putting the intersections of, I mean, I agree it's a little bit weird to put the empty set here, and I want to do it, and the reason is here I'm intersecting only one hyperplane, and so I get things that are two-dimensional. These are intersections of two hyperplanes, so they're one-dimensional. These are intersections of three hyperplanes, so they're zero-dimensional. And then you go 3, 2, 1, so you say, okay, let's intersect 0 hyperplanes. If you intersect 0 hyperplanes, then it's like you're putting all of R3 here. So, I mean, this is more or less the reasoning behind it is just to complete the picture, but it is kind of arbitrary to put it there.
So all those hyperplanes are contained in R3.
Exactly.
Yeah.
So,
That
right.
depends
So
on-
that is what I'm saying, that all of these hyperplanes are contained in R3, and that's why I draw edges. What's the idea? The idea is that this guy is geometric. This is a geometric picture that I am completely unable to draw. But this is a combinatorial picture. So the elements are combinatorial elements. The relations are combinatorial relations. And so this is really a combinatorial object. Okay? And depending on how much faith you have in this construction, whether you think this is a good construction or not, well, the natural question that you want to ask yourself is this good for anything? Can I tell anything about the geometric picture by looking at the combinatorial picture? That's the main question. Right? Mm-hmm. Otherwise, this is completely useless. Question, what can I tell something about my hyperplane arrangement A, which is a geometric object, from my intersection poset LA, which is a combinatorial object. Hopefully the answer is true, and then we can just do combinatorics on this guy and derive things about geometry. What things might you ask about a hyperplane arrangement? What kind of geometric questions could you ask? There's different things, but for example, you could ask yourself, in that picture, how many regions are there? Regions. So in this geometric picture, I throw in a bunch of hyperplanes, and so I get a bunch of pieces. And even here, it's hard to see how many pieces there are. Inside the tetrahedron, there are 2 pieces. Outside, I don't know, can you tell me? I don't think I can. So for example, can you say what the number of regions is? It's a completely geometric question. Can you say how many of the regions are bounded? So here you have 2 bounded regions. Or if you want to get even fancier, you could just ask about topological invariance, like fundamental groups or homology groups or things like this. Topology. Can you tell anything about the topology of the arrangement just by looking at this combinatorial picture? And the answer is amazing. It's yes, 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 yes. You can tell the number of regions. You can tell the number of bounded regions. You can tell the topology. There's a lot that you can. Yes, I can tell a lot about hyperplane arrangements from their intersection poset. Something that you should not at all expect. Because I start with this geometric picture, I make this other picture. But really, a lot of what hyperplane arrangement theory is about is ask yourself questions that are geometric questions, topological questions, algebraic questions, analytic questions. And try to see if you can translate your questions into questions about this combinatorial picture and just play combinatorics with an object that you can actually look at and compute things. So what we're trying to do, the next goal is just to do this for any matroid, not just for hyperplane arrangements, and see what we can say about it.
So flats refers to the hyperplanes.
So this is what, in this case, is called lattice of flats. And flats in this case are all the intersections of hyperplanes. And we want to do this not just for hyperplane arrangements, but for any matrix. All right, let's stop there, and I'll take questions. I mean, I'll stay. But stop there because I'm out of time.
I just think it's hilarious because I hear people say that all the time. It's so twisted up and backwards. Like you would think people would say vertex is okay. It's like when I hear